Hi, Algebra 1. We are heading into Unit 2. This is starting out Lesson 2, Writing Equations to Model Relationships. This is Part 1, so here we go. To start out here, we're looking at these three figures, a tetrahedron, a cube, and a dodecahedron. And your job is to just figure out in what ways are these three figures alike, and in what ways are they different. Go ahead. In this unit, we will constantly be looking for patterns. So in number 1, when you're looking at your two observations, you're looking for any patterns you see between the number of faces, vertices, and edges. For example, one pattern would be that there's always more edges than there are vertices and faces individually. Another pattern might be that if you add together the number of faces and vertices, it's always more than the number of edges. In number 2 here, they're putting some algebraic notation to those patterns that we just noticed. Similarly, just like we noticed there's always more edges than faces, they're saying that the number of edges is greater than the number of faces. And just like we noticed that the number of faces plus the number of vertices is always greater than the number of edges, that's what they're saying right here. They're just saying that it a little bit backwards. They're saying the number of edges is less than the number of faces plus the number of vertices. Now, there is a relationship that can be represented with an equation. That means using an equal sign. So can you find it? I'll give you a hint. It does involve adding together your number of faces and vertices and then eventually getting the number of edges, but there's a step in between. Maybe you notice that if you take the number of faces, add together the number of vertices, and then subtract 2, that you always get the number of edges. So as an equation, we could write this as the number of faces plus the number of vertices minus 2 always equals the number of edges. Here we're going to start writing some equations to match these descriptions. We're going to do A, B, and C together here. Blueberries are $4.99 a pound. Diego buys B pounds and pays $14.95. So I could write that as $4.99 times B is going to equal $14.95. We don't have to solve it. We're just writing the equation. In B, we know that the blueberries are $4.99 a pound again. Jada buys P pounds and pays C dollars. And in C, blueberries are D dollars a pound. Lynn buys Q pounds and pays T dollars. All of these different letters we're using to represent things are variables, and hopefully you start seeing a pattern as you write these equations. Go ahead and try D, E, and F. The big thing in these three equations was that in subtraction, the order matters, and so they have to be in the right order. So 275 minus n has to equal 45, similar in these other ones. Ask questions if you need help. In number 2, hopefully you notice that our equations are really similar as you go down A, B, C, and then D, E, F. The only things that are different are that we are including more variables because we have more unknown amounts. In activity 2.4, car prices, we're going to put together some equations here that are incorporating a few more pieces than we've been seeing. So the tax on the sale of a car in Michigan is 6%. As a decimal, just as a reminder, that would be 0.06. At a dealership in Ann Arbor, a car purchase also involves $120 in miscellaneous charges. That's a flat fee no matter which car you buy. And so there's lots of things to take into account: the original car price, the tax, the miscellaneous charges, and the total price. So we're going to write an equation to describe this relationship. So starting with A, if the original car price is $9,500, we're going to pay that. So there's our $9,500. Plus we have to pay 6% of that. Of means multiply. So we're going to pay 6% of or times that original price. And then we're going to pay $120 in fees. And whatever that's going to be is going to be our total price that we're going to pay for the car. So skipping down to D, if the original price is P, our equation will be that we're going to pay the original price, plus we're going to pay 6% of the original price, plus we're going to pay $120, and that will equal our total cost. Looking at number 2, how would the equation change if our sales tax was R% and our miscellaneous charges were M dollars? Now, looking at this equation here, we would still be paying our original price P, We don't know the rate here, so we're going to call that R for sales tax. We're still going to take that times P, our original price, and instead of 120, we're going to have M dollars being our miscellaneous charges, and that will still equal T, our total cost. Here's some things I want you to add into your glossary. It's right at the end of your lesson. The term constraint is referring to a limitation on the possible values of variables in a model, or that means like our equations. And what's that saying is that some values, for example, have to be positive. So like this example, a distance above the ground D might be constrained to be non-negative or positive. So we would express that constraint as D has to be greater than or equal to 0. The other term I want you to add to your glossary is model, and that's a mathematical or statistical representation of a problem. So that's going to include our equations that we're creating, or when we graph equations, that's a model, or when we make a scatter plot coming up in Unit 3, that's going to be a model. All right, Algebra, nice job with this lesson. You're ready to keep on cruising to your practice problems and then on to Lesson 3. Keep going.